Hello there.
How are you?
Fine.
Beep, pop, boop. Welcome to another video. Today we're going to make a little game in ReScript and KAPLAY. ReScript is a typed programming language that compiles to JavaScript. It offers features like static types and functional programming, which of course I like. KAPLAY is a really interesting canvas game engine. It has like batteries included and it handles much more than just rendering your game on the canvas. It has features like collision detection, physics engine, and it solves a lot of the default challenges you have with making a video game, and it does it out of the box so well. This is not really a tutorial for either KAPLAY or ReScript. Both have a great website with good intro and good documentation. I'll add some links to the description. For KAPLAY, I can recommend the videos of legendary JS Dev. He really nails it when it comes to explaining the whole flow of a KAPLAY game. All right, buckle up, let's go.
Give me the meat and give it to me raw.
Let's create a new ReScript app. We can do that via button create ReScript app. I'm going to use the add next because I want the V12 version to work. So this is a little prompt that will scaffold our ReScript application. So I'm going to give it a name, which is going to be Snake. We're going to build a snake game today. As for template, I'm going with basic, but we will be using Vite. A bit more on that later. Now, as I mentioned, I want to use V12. This probably is the last alpha. Maybe there's one more alpha, but it's soon-ish going to be in beta. So I do recommend each new ReScript project you create to start using V12 if you can. And that's it. So let's fire this up in Cursor. Okay, you can see in our package.json we have ReScript installed. We're also going to need to install KAPLAY. So let's do that via bun install KAPLAY. Now we have both our dependencies, so that's good. Our ReScript JSON is kind of the file that defines where our source files in ReScript are going to live, and we are having the source directory over here. We have a demo.res, so let's maybe just rename that to game. And if we compile them, it's going to have the res mgx suffix. Scaffolding comes with a couple of snippets. So there's a res build clean or def. Basically, we want to target a ReScript compiler and just execute ReScript. It sees all the files in the source folder and potential dependencies that you have, and it will have created that. So that's great. Now, what we're typically going to do in a game is compile the ReScript in one terminal, and then you use another for a potential dev server. So in this case, I mentioned that I do want to use Vite, so I'll install that as well. And the reason I didn't go for the Vite template is that also brings in React and Tailwind, and that's just a little bit more than we actually need today. So what I am going to do is create an index.html over here. Then we can just scaffold it, say it's our snake game, go for a script, and we have some autocomplete by Cursor, but I trust you, this is not a tutorial on AI or anything, so we're not going to do anything fancy with Cursor today. That's not what this is about. I'm just been using it and it works well for me. That is actually enough to get a dev server running, so you don't necessarily need a Vite config. If we just do bunks Vite, so bunx like npx Vite, then we have our dev server already running. What I'm going to use today is the simple browser. So that's the browser that's inside of VS Code. And right here, we can't really see anything, but we should get a log of hello world. So I'll switch over to my actual browser just once so that we can see the log, but then let's just keep on moving. So as I mentioned, we're having this open in the browser and we can see our hello world. This corresponds to our file over here. And this is where we're going to load the KAPLAY game. So out of the box, ReScript doesn't know anything about KAPLAY. So I already kind of went ahead and create some KAPLAY bindings. Let's just briefly go over this. This is a bit more than what we need today, but I'll just give you a rundown of the basics. You get the default KAPLAY function from KAPLAY, which we can annotate with this module. So this module corresponds to the module over here. We'll create a KAPLAY game object, a game context if you want, and we'll do everything with that context. So we'll need the context to render something on the screen, etc. So that's like the important thing, and that typically is a singleton as well. So every single context, we're going to create that with some potential options, and that object creates a play context, and then you'll see that there are like a lot of helper functions, and they all really much take the play context, and then you can do something. So we're going to use vectors, there's colors, all these kind of things. So that's yeah. Those are kind of the bindings. I went ahead, I'm going to gloss over all these. This is a approach to it, and I'm not quite sure if it's the right one or the perfect one. So that's why I haven't really published any of these things on NPM. For our little demo today, this is going to be good enough, and will just definitely give you a sense of what KAPLAY means. So as I mentioned, our KAPLAY context typically is a singleton. So we're going to create a game context so we can reuse that later in different files. Open KAPLAY indeed. So let's create a single KAPLAY context. We'll pass it some initial options where we're just going to hard code some things. The width today is going to be 500. That's in pixels. The height is going to be 500. Cursor is a little eager when it comes to all these things, but we'll start here. And yeah, let's maybe for like a background. So background takes in a hex color here. Let's go with something F1, F5, F9. So that's going to be something grayish. All right, so this compiled to our KAPLAY context, the default function I mentioned. And if we now use this in our game, so we open KAPLAY for the bindings, we open the game context. Very simple. If we were to just do like a simple log of the K that we have here, we should now in our simple browser see our gray background. So this is going to be our game canvas. We're also going to have like a lot of constants. So I wanted to create a constants module here as well. So just split that and we can see the game and browser. The constants aren't really that interesting, so I just prepared them. This is our game size, so this is the 500 matching the KAPLAY. Constants does want to use the game context, so we can't create a cycle. We cannot use the constants in the game context because the constants use the K instance over here a little bit later on. So that's a bit of a trade-off, but this is like the only thing we're hard coding, and all the rest will sort of inside of our game will use our constants. So we have a game size. We're going to have like a tile-based game. So we're going to create a snake. The snake is going to be just a little block really. And the block is going to have that kind of a size. And it takes the entire tile. But yeah, you'll get the gist later. We'll have a couple of tags and scenes. These are variants, but you can sort of consider them as enums right now. And then we have some colors. The color names are just like based on Tailwind color names. Then maybe that's less descriptive towards our game, but at the least I know like where this is coming from. We're not going to use Tailwind, by the way, but you know, just color names. So in our game, we're going to create a couple of scenes. We're going to create two scenes, which is the game itself and a game over scene. And you can sort of see this into two different screens, which we can switch to. So a scene is nothing more than a separate function to really wrap everything that you want to load inside of one scene. And you can like load another scene and be more efficient about that. So this is just a unity unit. And then we can do k.scene. And here we're just going to use the constant game and the game itself. Now this takes a string, but because our variant doesn't have any like data, we can just really coerce it to a string. This is another one of those things that I'm not sure if that's the right way to do the bindings, but that's what we're going for today. And this is our game scene, but of course we need to tell KAPLAY to go to that specific scene, which we can do like now. Nothing really changed, but it is hitting this function. What I can do here is there's a debug in KAPLAY, so we can do like a k debug and then debug log, where we say game launched. Yeah, so you can see the game launched, so that's fine. And inside our game, we're going to use various things called game objects, which is a composition of different game mechanics which you want to include in certain objects. And this is where KAPLAY really shines in my eyes. Like, it allows you to really compose the behaviors you want inside of a game object instead of going into some like object-oriented inheritance kind of thing. You just really, it's plug and play. You take what you need. So in the first case, what we're going to do is going to create some borders here. We're basically gonna create a wall, and to do that we're going to create like a wall object. So what we want to do here is create a new wall res. For the wall we are going to need certain components. It all starts with an abstract type T, so this is like our game object, and we're gonna do the functor thing and include some capabilities with some additional functions that you can call with that abstract type. So this on itself doesn't really do anything, but it's used to pass on into different modules where the magic comes from. So one of these things, like a wall, will need a position. What we can do here is say position, and it all is position components, where here we need to give it like a module signature. So this is passed into the module. And if we take a look at this accepts like a type of T, and then it adds functions that take that T and allow you to, for example, like move the game object or know the world position, update the position, getter, setters. So yeah, a couple of those things. And then this will add our positions and create a, again, abstract composition type, but these are like the shared building blocks which will accept your input to construct an actual object. So we'll get to that, but basically here we're adding everything that it has a position on the screen. We also want to create a rectangle, so the wall has something that's like actually drawn on the game screen, and I want my wall to have a separate color, so that's gonna work out as well. We're going to create a make function where we just pass in some initial data. So we're going to create multiple walls, so that's why this is parameterized. If your game object is really only going to be created once, then you might not be interested in taking everything as parameters. It really depends on the situation. But in this case, what we can do is we can say KAPLAY.add. So this is like the top level game object, which are, well, the context sort of acts as the roots thing, and it will take in an array of composition. And because we've included these compositions, we can call helper functions that sort of add each composition. So what we can do now is like say add position, this takes the K, add a rectangle, add a color. So my gray already is a KAPLAY color. So if we just go back, the constants here already calls the wrapper function. This returns a color of T, which is the thing that the color composition takes. So yeah, we're basically creating a new game object. We're telling what we kind of want the behavior to be, and then we have a function to make the walls. So we're going to create our wall in our game, so we're going to do that in our scene. So I'm just going to say like top wall. We're creating a top wall. We're saying that the X and the Y are 0. So all these things stop top left, as games typically do. Then we have a width, which in this case is the entire screen. We have a height, which is 1 tile size. And what I can do here is press F1, and then you'll see a little red dot here. So this is actually because we have a position to our wall. So this is our top wall, and we'll create some other walls here as well. Have a little snippet for that. And then basically our walls should all be there. The left wall, I have the right wall. I don't have the bottom wall yet, so let's quickly add that. And there we go. And these are our walls. These are actually purely visual, so they're just going to be here. We're not really going to use them. This is our first game object. We're going to create a couple of them and then sort of see how these interact. All right, the next thing we're going to do is create a game area. That's another game object where we are going to not really draw anything on the screen, but keep track where this center block is. So our game area is going to be like an invisible component. I'll just quickly paste this code in, and we're going to use the area composition. The area is the thing you use for collision detection. When we add an area, we can say what kind of a shape do we want, and we're going to say this is a rectangle. The rectangle sort of needs to have an offset, so this is this little offset, and so it starts over here, and then it just spans to this location and this location, where, you know, it's the light gray thing, basically. But we don't necessarily need to draw that on the screen anymore because the background suffices here. What we can do is when we create our game area is see this in our DevTools. So if I press F1, you can sort of see there's a blue rectangle here, and this is our game area. So we can use this game area later to check, is the snake still within here? If it hits over a wall, then we can say like, oh, you hit the wall, game over. So that's why we're using this game area. It's a bit of a simplification. I just figured out while recording, in hindsight, maybe we could have given this an outline instead of creating actual walls, and we kind of maybe had the same effect. So anyway, the script says we're going to hold with walls, and that's what we've drawn here. Next up is going to be our snake. Now we don't have our snake game object yet. Let's create that as well. For snake, we're actually going to have like a little bit of a snake part object instead. The snake head and snake body are slightly different, and we're going to sort of encompass the small details inside of the snake part module. So there's going to be a head part, and then there's going to be like a tail part. We're using position, so the game needs to know where the snake is. It's going to be a rectangle, it's going to have a color. And we're going to use the area composition for collision detection. The head of the snake will be used to detect the walls if it's still out inside of our game area. And of course, we need the head and the tail to sort of detect if they are colliding, because if the snake eats its own tail, then it lost the game as well. We're having a little constructor function where we call KAPLAY add, and we add all our different compositions. Most of this is, as we saw last time, position, rectangle, color, area. And here we're also going to use a tag, so you can tag certain game elements and then later do operations with those tags. Like, you can ask KAPLAY, did I hit any game object with a certain tag? And the tag is also a string, so we're sort of downplaying this. In our function here, is this going to be the snake head, snake tail, or later a coin? These are our like predefined tags, and we're using coercion to transform them as, or to see them as strings. So when I come here and I make my snake again, I have an X, Y, and a tag. So if I go snake part, put it over here, so this is top, and we're going to just center it a little bit. Yeah, so it's in the center here. This is our basic setup, and the next steps will be to add a coin, add movement, add collision detection, and yeah, build our snake game. Now I mentioned that ReScript does functional programming, and that typically means that everything is immutable. So everything you declare as like a let binding is by default immutable, but we are going to mutate some states. That's typically what's being done in games. So what we're going to do is we're going to create a game state over here. The game state will have some mutable stuff. So like, when was the last time that we updated the screen? So we're gonna have like a scheduled interval when the snake moves. We are also going to have a certain speed to this, and we're gonna have a current direction, which is gonna be a vector 2. We're gonna keep track, where is the snake going? Is it going up, down, left, right, etc. And every so often we'll have like each time game speed has been, the threshold between game speeds will kind of determine that a move must be made, and we're gonna keep track of the last update time. So this is the delta time, like how many time in game has passed, and then do some calculation with the speed. What we can do now is add an event listener on update. KAPLAY has this on update, where we can pass in a callback, and the callback does return a controller. We won't need this controller, so we're just ignoring that. We can ask for the delta time, like how many times has passed since the last update, which is k.dt. And then we're just gonna say the game state is the last update of the game state is going to be the game state plus the delta time. We don't have a game state yet, we just defined a type. So what we're going to do is we're going to have something reset game state, create like an initial game state and just create a new instance of that every time we start the game. Because if you lost the game and you were, at a very low speed or something, then you basically want to reset the whole thing and have the experience consistent each time. This is a little helper function that creates a game state. We're going to use one game state inside of a game, but then when we switch to game over game, we just want to reset that all the time. That's okay. For the current direction, we need to pick a direction, and we should try and go into that update again if we need to update. So if the game state is indeed higher than the speed, then we are going to do some update mechanic. We're basically going to see what is our next move, and that will be the game state dot current direction. So the direction is a unified vector, and we're going to multiply that. So we can call the scale and then just do constants dot tile size vector. So we're basically, it's going to the right, and then we're just going to scale that until go to the right for like an entire tile. So that's what that does. So that's our next move. Our next position will be to grab the snake. So we can remove this underscore over here. We're going to say snake dot, and then you can see a snake part should have a get position over here, where we're going to do vector2.add of the next move. That's going to be our next position. We're going to say that our snake, which kind of is our snake head, so let's quickly change that name maybe. The snake head is going to be set to the next position. And of course, because we did something, we'll need to update the game. And they can see every so often on an interval frame, we are going to update the game, but of course the snake is just moving in one direction and can't really trigger anything. And there's also no detection being done whether it's still in the game area or not. So next would be to support all the arrow keys. And what we're going to do is create something called a direction map, where we're just going to create a map from array, because we're not really interested, not all key presses will do anything. So this is just a way to say that the up key, which is part of our KAPLAY bindings, is going to map to a vector up. So we're just mapping key presses to vectors here. And we're gonna add another event listener after our updates on key release. So this is when you let go of the key. This will take a key. It also returns something which we don't care about. So it's like a controller if you later want to remove that. And what we're going to do is a map that get the key from the direction map. If no key was found, we don't really need to do anything. If a direction was found, direction map. If a direction was found and we actually get a vector, then we're just gonna update our current direction to that vector. So over here, and I need to switch these around so it takes a direction, it takes the map first and then the key. There we go. If I now press up, then you can see we're going up. If I press left, etc. But of course, there's a bit of a gap. Like I can press a lot of keys at the same time. Like what should it do then? And I'm going to the left right now, but I can also go to the right. And that's something the snake cannot do. It just cannot do a 180. So we'll need to think about a mechanism to sort of capture this, what happens when you press multiple keys, because this is just going to be called on every key press. And what can we do to prevent the the snake to do the 180. To do that, we're actually going to batch our movement. We're going to create a new data structure over here, which is going to be the queue. So I prepared a little queue thing here. This is very simple, it just takes an array and it's going to take a max size as well. We can enqueue if something is being added. So if the queue is full, we're just going to remove the oldest item. And in this case, we're going to dequeue in our update function, and we're going to take a peek inside of our key press. And we'll see that, oh, if you're going down, but you pressed up, then we're not going to accept that key. That's basically what this peak is going to do. So in our mutable game states, we'll have to add the direction queue. So that's going to be of type Q, which we just defined it as a separate module. And it's going to take a vector 2, which is basically, going to map to these vectors. And for our direction queue, we'll just need like the last 3 key presses. I think that's going to be enough for checking that out. Now, I told you about the 180 situation, so let's just create a helper function to deal with that. And we can say our opposite vectors, which we're very naively just going to, this is a very simple check. So in this case, if we're going to the right, our x will be 1. If we're going to the left, it's going to be -1, so that's going to check for that. And otherwise, 0 is still 0, so that's fine. Now what we want to do is when we release the key, we are going to think about what is our next direction. And herefore, we're just going to switch on the queue.peak of that game direction. So we might have already pressed the key or we didn't. If we didn't press the key, let's just use the game states at current direction. So that's going to be our next direction here. And now we can do an additional check if we press the key and it maps to a direction, a vector, like are those not on the opposite side or not? So basically we sort of, we had left, we pressed right, and then we're going to check only if those are not on the opposite side. So we're checking the direction we had, the next key we pressed, and then we're just going to update the current direction. No, that's not current. What we actually want to do is enqueue the next direction. And otherwise we don't want to do anything. This prevents the actual key press situation. However, I can still bypass this. So even though I can't press left, can't see it, but I'm pressing left and it's not being queued, I can still press other keys and eventually press left. And because of the 3 size limit, it can still subsequently get the opposite direction of where we're currently going, can still be sort of interlocked here. So we'll need to like do another check in our update function as well, so that we don't get to that point. Here we can do a switch of the game state .q direction, and in this case we can dequeue. And if nothing was pressed, then we shouldn't do anything. Then the current direction still is the right call. Or if we have something queued up, the direction, and here again, same check. If our opposite directions, which is the game state current direction, if that is not the case, then we can say that the game state dot current direction should become the next queued direction. I can now, so I'm trying to get to the right, I press 2 keys and it really queued up the movement nicely. It processed 1 direction per interval, which we do here, and that nicely did our movement. So next up is gonna check when we no longer are inside of our game area. We do wanna like end the game. What we're going to do now is create a little game over function over here, which is a callback. And yeah, let's just do like a debug of game over. Basically, you're gonna hit the game over when you either eat your own tail or when you are no longer in the game area. So that's why we're just already using a function right now, and then we can call that twice when we need to. So in our update, when we have our next position, before we actually set the position over here, we're gonna do a little check, and we're gonna say if the game area, which probably has an underscore still, there we go. If the game area has a point, and that point can be a vector, so that's going to be our next position. Then we can update the snake because we know the next position is still within the light gray area. Otherwise, we're just going to call game over. And when we hit this, we see game over, game over, game over. So our update loop keeps on progressing. So yeah, that's why you want to go to like the next scene and maybe do that. So we're eventually gonna solve that, but it doesn't really stop the game. It just doesn't stop moving anymore, and we're in this game over. But it really still does the direction, the loop every time. It calculates the same result and then says game over. So let's just remove that for noise. Let's now create our coin game object. We'll do coin.res. There we go, have another snippet for that. So we have a position, we have a rectangle, we're gonna have a color and area. We're also having a z comp. This is like a z index kind of thing, like you might know from CSS. Not sure if we actually still needed that. The reason I originally introduced that, or the script has it, is that your snake you want the snake to go over the coin, and potentially that doesn't really happen, and you sort of go under the coin, which is kind of weird. So that's where this Z component comes into play. We're only going to have one coin at a time. So what we can do is we'll create a random position and just pass in all the objects over here. And we don't actually care about the coin object. We'll use a different mechanic via the tag later on to really see if collision happened or not. So we have a rectangle, it has a color, it has a position, it has an area, things that we saw. The random position is really just some math to get the game size -1 tile, because that's where the wall is. And then we just do like a random function which KAPLAY has. So it's going to be between the starting point, which is 1 tile removed from the border screen. It has a random x, and we need to ensure that it's, it's a multitude of our tile size, so that's where this modulo thing comes in. This is a little bit of just, math. I'm gonna gloss over that, but that's basically our game. Now to spawn the game, to spawn the coin, we are going to just call the make function at the end. Coin.make. And that spawns our game. Inside of our update loop, when we checked for game over, we're also just gonna check for, do we have any game objects? So I can just top level ask KAPLAY get game object by tag. We can just ask them, do you have any objects with a tag? Just gonna return an array with objects. We know we actually have a single coin, and we can also just add like an additional condition. Coin has point. If the coin that we're grabbing here has the next position of the snake, then in this case, what we can do, if that's all not the case, we'll do nothing, of course. Here we can say coin.destroy. We can increase our score. So that's going to be game score. I don't think we have that yet. And we just call the coin make again. And then the coin destroy doesn't need the unit, and we don't have the score yet, but you get the idea. So mutable score, initial score is 0. And if I now capture the coin, you can see that it spawns in a new position, and I actually have 2 points now. The game stops, so nothing can happen anymore. However, we don't really see our score just yet. So we're going to create a text component to actually see our score. This is another game object. I'm going to use text a little later. So we're just going to create like something rather generic. So we go text.res and another snippet. So this is all rather the same, except that we now have the text component, which is the thing KAPLAY uses to render text on the canvas. In our make function, we have this add text, which just takes in the text. We're gonna give it a size, an X and a Y. So we're gonna use that in our game over scene as well. It's a little bit reusable. We are using the anchor component. That's really just to center things. It's gonna be easier. The anchor, if you notice the little red dot, that's your anchor. We're gonna use. You can also move the anchor with the anchor composition. In our game, we are going to create the score text, score, and let's interpolate the game score. So int.toString. Every every hole in an interpolated string needs to be an expression as a string. As for the size, X and Y are going to be using our anchor, so that's why we want it in the middle of our screen. So it's going to be the game size divided by 2. The Y is just going to be the game size plus an additional tile. There we go, and now we have our game score. However, our score is going to be like here, and we'll need to update our game context to just include like one more tile over here. There we go, and now we have the score. That's not quite right, so maybe 2 tiles, maybe I sort of figured it like that. Let's remove our game launch. We kind of know it launched. And if I'm now going to hit a coin, that's going to increment our score, but it's not really going to increment our label. So we'll need to do that as well. So here, when we have our coin, we're going to say score label. And if I now go for the coin, you can see that the label updated. So that's pretty basic stuff, but you can update the score text because of the text components, and then you have the set text over here. Okay, so the next thing would be to create a game over scene, which is basically another scene, but scenes can take a parameter. So we're gonna pass in the score of the last game, and we're just gonna make some text, game over. We're gonna show the score again, and we're just gonna have like a click to play again. So we first define another scene, which is our game over. And then when we had our game over function, we are going to actually just do k.go constants.gameover, so that's 1, but then we do need to pass in the game score. So I'll do score over here, score over here. This is a label, so this is data, but now our game over, yes, game over here should accept our game state score. Oh, this is perfect. So it's going to create a first point, game over, and then our score was passed to our game scene. And when we click to play again, we just go back to the game scene. So the click goes back and it starts all over again, and it has this resetted game state. So that's perfectly fine. Okay, so now we have our snake. We don't really have a snake tail, so when it eats coins, it does not really grow or anything. So we'll need to create some snake parts as well to create the tail. And I already have this snake head, so let me create a snake tail as well. For the snake tail, this is going to be an array. So we can say array from initializer. We are first gonna start with length 2, and then we have like a function callback. So it's gonna have an index, and here we're just gonna say snake parts.make. Actually, this is another interesting thing you can just do with ReScript, which you can in JavaScript, which I really like. So we're going to just create an entire expression. Over here, we can have that head position. We can just say that, okay, this head position with X, then do the thing with the index times the tile size. Because this is an int, we're basically doing the to float. And then over here, what we can say is most likely the head snake head.y. We need the head position instead of the snake head. Sorry about that. So yeah, you can see this created a tail, and the tail moves to the right. So it's the head moves to the right, like a slightly different red. We probably want to do the minus thing. Yeah, there we go. Next thing is just move the tail when the head moves. So we'll need to do that. And this is surprisingly easy. I kind of figured this would be a little bit more tricky, but that's not really the current case. What we'll do here is in our update function, let's just grab the current position of the snake because we need this later. So for the next position, current position, add the next move, etc. And when we move the head over here, we are going to move the tail. And we can do that with a reduce. So we're going to reduce the snake tail. Let's say tail parts. And we're going to say the next tail position is just basically the last one. So we don't need the last tail position as a result. It takes in an initial argument, which is the current position. So it takes in the position of the head, and it's going to go over all the tail pieces. The first tail piece, we're just going to store that position to later on give to the next tail piece. And we're going to give the position of the head the first time to a tail part, and that's sort of how the snake moves. And if I press some arrow keys, that's actually all there's to it. So that was definitely kind of neat. But what we of course now see is that we are eating a coin, but our tail isn't getting any larger. So that's also something that we need to do. And what we can do here in the coin, when we ate a coin, we can say that snake tail, we can just call array.push. And we're going to just use like the current position of the head. Wait for the next one. And so it eats the snake, and when it's one move beyond that, it's sort of going to grow, which is good enough for now. And then lastly, after checking whether we ate a coin, we do need to see, did the snake touch the tail, or the snake head touch the tail. So here we're going to do a snake tail. If any of those tail parts, so array.sum, so we're going to basically ask it has point. And that's also again going to be the next position. And if that is the case, we're just going to do a game over. So initially I can't eat my tail because I only have 3 pieces. I ate one, and yeah, a little tricky to see, but I just pressed enough keys so that it went into a circle, and then I ate my own tail, and I have a score of 1. We are almost there. So if you're still with us, thank you so far. And yeah, the next bit would be to add a good position to the spawning of the coin. So inside of our coin, we created a random position, but what if that position is placed directly on one of the snake parts? Then it's going to be a little bit confusing, and that's really not what we want. So we are first going to add a little helper, is good position, which takes in a position, and we're going to need to check whether the snake head has the position. So we're going to pass in these things over here, the snake head and the snake tail. We don't need to really specify the types over here, because the first thing we're going to do is we're going to use a snake head and then the module. So if we do snake part, then the compiler will sort of figure out, oh, but this is a snake part, because this is it's going to infer that. We're going to do the has point, so of our input position. And so it should not have our point over here. And it also should do the same for the snake tail. So instead of some, can probably do ever. Yeah, let's do maybe every. Over here, add some parentheses. So basically the snake head doesn't have the position, and all of the snake tail parts don't have the position. Then that is a good position. So over here we have like the random position. Let's do something like recursive coin position. So we're just going to create a random position, and if it's a good position, return that position. Otherwise just call itself again and try again. So over here we have our coin position. We changed coin, we didn't change our game, so that's probably our problem here. So for a coin make, I need the snake head, the snake tail, and call that at the start of the game as well. So there we go. And well, you can't really see it, but I mean, we fixed it. So the absence is going to be the proof here. Okay, to wrap it up, we're going to look at how can we increase the game speed. And this is really a little bit of a game design thing. So what we can do is every time we add a coin, we can say that the game speed, I actually don't need this dot anymore. This is a ReScript 12 thing. So these are two floats and I can just use like a regular minus. So we're basically going to say that, oh, our game speed, I don't really know what the good value is right here on top of my head, but we'll just pick something and we're just going to update that. We eat another one and you can see that we're picking up the pace. Yeah. So yeah, this wasn't a good value or anything, but you get the idea. Like this is also the point where we update the game speed, and that's our little game. So
Yeah!
thank you so much for sticking till the end. If you found this video interesting or entertaining, please consider leaving a like. It really helps the channel a lot more than you think. And until we meet again.